The story of the origin of Yara is the story of two men that met at a dinner party in Norway over 100 years ago. Together, they created the foundation for what feeds today over half of the world's population. And it all started here in Rjukan, Notodden, Norway. By using hydroelectric power to extract nitrogen from the air, the curiosity of Christian Birkeland and the ambition of Sam Eide not only created the basis for large-scale mineral fertilizer production, but paved the way for the industrialization of Norway. Mineral fertilizer meant famines in Europe could now be averted. Within a decade, mineral fertilizer was now being exported to Asia. The occupation of farming became more viable and more profitable than ever. Today, we are facing even bigger challenges. Our determination in solving these challenges is stronger than ever.
To contribute to a more sustainable planet. That is our goal, to do more with much less. A more sustainable agriculture through the efficient use of resources. Our effort is based on efficient use of water. We promote the development of technified agriculture, seeking to deliver in each drop of water everything necessary to achieve higher yields and superior quality. We provide products based on potassium nitrate that help reduce and have a network of experts around the world. We are driven to make this red the sweetest you have ever produced. This orange of incomparable flavor. And this green, the most natural you have ever grown. We are committed to this challenge, to contribute to a sustainable agriculture. SQM.
Thanks for the opportunity to join the webinar on potatoes. It's a privilege and it's a really delight for Yara and myself to share our knowledge with everybody. Welcome to our audience, our attendees from South Africa, and I see there's also some attendees from abroad. So yes, welcome. Getting on with the presentation, there's the content of the presentation. I'll do introduction. It will be a bit more than an introduction, but give you sort of an holistic view and perhaps having a bit of a look in the crystal ball of what's happening in the future, and just taking that from facts that's already there. Looking at concept of yield gap analysis, and then going back to water or irrigation, seed and nutrition, looking at balanced nutrient applications, all the elements that you see there, and yes, then later a conclusion. As I said, looking at mega trends, challenges, and what probably with the information that we have now, what the future is holding for us. Just for our viewers or attendees from abroad, data producing areas or regions in South Africa, you can divide it in a northern and a southern part because of the climate conditions that varies. To the south, we have the winter rainfall areas, and to the north, the summer rainfall, and also the type of soils and conditions, other conditions that you have to the south and to the north. It varies a lot. To the south, more sandy type of soil, and to the north, the more better and stronger soils that we have there. I'm at this stage around about here in the Sandveld area. This is where I normally work and spend my days. So this is the areas that we have. As I said, Sandveld here down, Cape area, and then going up north to the Free State Limpopo in the northern provinces up there. Moving on to the market shares of the different areas, you will see that Limpopo do have the largest market share, followed by the Free State. Take both the Free State areas, you will see that they are probably the biggest area. Say the three of them do have the largest share, and they do provide potatoes right through the year. Interesting here to see is that South Africa doesn't store any potatoes, potatoes for fresh consumption. There's always fresh potatoes somewhere in the country, enough for all the markets. The only area that's producing potatoes right through the year is the Sunveld, where the other areas do have a break in production. Now, in a certain sense, there's some pros in that, but a cons is that you will always have green potatoes somewhere on a field, and that's not good for pest and disease management purposes. So, on the fresh potatoes that I've just mentioned, 75% of all potatoes are fresh, and the rest is for processing. So processing industry not that big as what you will have in the European or American countries. This slide emphasizing on what I said in the previous one is on the hectares of the different areas they cover, and if you look at the top four of them, you will see that they about 70% of the total hectares are planted in that areas, and that's in Limpopo, the Free State areas, and the Sunveld. The top 70%, or the total of 70%, and as well as with the amount of potatoes that's produced there. Total about 52,000 hectares for South Africa. And if you look at the total, the bags, the 10 kilogram bags, you will find that our average is around about 50 tons per hectare in South Africa. The next slide will show you that have taken place in the last 30 years industry. If you look at hectares and crop size, you will see there was a huge increase in average yield per hectare, but that is from, if you look closer, you will see that there was a shift in from dry land production towards irrigated areas. That's what have taken place, as well as new cultivars that were introduced. And of course, efficiency and productivity, let's say the producers, increased as well. So firstly, more irrigated areas, more water usage, groundwater, as well as dams and stuff like that. So we do have more water use, higher water footprint that's involved with this increase in production. This is a bit of a sad story, if I can say it like that. You will see that production costs in the last year increased a hell of a lot, and I think it's between 50 and 60% from last year to where we are now. You will see that irrigated areas from Northwest Province towards Sunveld, they are near 300,000 Rand a hectare at this stage, and that's excluding owner remuneration, land rent, capital expenses and stuff like that, interest and so on. So that's not the total. So if you look at that and you look at the average yield for that areas, you will see that the guys must get now about between 50 and 60 Rand a 10 kilogram bag of potatoes just to break even. So there's a hell of a lot of a cost squeeze at this stage on potato production in South Africa. One of the big contributors is fertilizer. I did have a look at fertilizer costs for the Sunveld, and I think that's a little bit high, decreased by about 15,000 Rand. But I got these numbers from Potato South Africa. I have a talk to the economist there and see if how he did that calculation. But still, it's really high, and I think at this stage, producing potatoes in South Africa must be one of the most expensive countries in the world to produce potatoes. So that means we must just be more vigilant on our risks and things that we take, not going too far with that. And our productivity must be as high as ever, and don't take any risk at this stage. Good. Going a bit more global and looking into the future, this is trends that we will see happening in the next 25 years. 9 billion people on the planet, hell of an increase. We will need more food for them. But with that, an increase in greenhouse gas emissions. And that's sad. Again, that's something that we don't want to have. We actually want to decrease the greenhouse gas emissions by 40 to 70%. Of course, if we don't do it, we will get that global temperature will increase more than the 2 degrees that we have in mind. And with the increase in temperature, we know what will happen then. So this is trends that we have to keep in mind. And I've talked about mega trends. So we will need more food. And there's also a shift in the dietary of the way that people eat. They don't want to eat maize or paddy rice or something like that anymore. They were looking at food like potatoes. So something that we will have to keep in mind. But we will have to be more efficient, and I will later talk in a few slides about yield gap analysis, where we must focus our attention in getting to this number. This is just a fact. They say that in the next 50 years, farmers will need to produce more food than they have been producing in the last 10,000 years combined to support the growing world population. And this is just staggering if you think about that. In 50 years, you have to do what's been done in the last 10,000 years. So really, really a challenge. Companies like Yara and SQM, they are seeing it. And what are they doing about it? Like Yara started off, as they said in the video, more than a century ago, and they were more in the area of a wholesaler, producing for Europe, and they start expanding, not really on farm level. They were a wholesaler, and as they've moved along, you will see that they have moved now, this global company, towards a nature positive solution. So from a wholesaler, and if you look at the left bar, closeness to the farm and the food companies, they were sort of on their own and moved closer to all other input suppliers, food chain partners, and closer to their end user, the farmer, looking at things like nature positive solutions. And we will later come to that again. But things like carbon footprint, it matters now. Being more efficient, giving more efficient advice, new innovations, bringing that to the customer. That's the issue now. So at the left, you will have Yara's mission: responsibly feed the world, protecting the planet. And this is the 5 or the 7 key mega trends in our strategy. And I've talked about the shift in dietary demands from needs from the customers and the consumers, but also looking at reducing greenhouse gas emissions, looking at water, looking at safety. And I will later, just at the end, talk a little about soil health, the new age that we're in, and they're talking about the 4th industrial revolution. So it's a digital and technology revolution, and that's also coming to the farm and affect our productions and supply chain. I mentioned that we will need more food. The top 5 crops currently globally that's produced is sugarcane, maize, paddy rice, wheat, potatoes, and that's negotiable. This increase in food supply will have to come from somewhere, and it will be this crops that we see here on the screen. And you can plantain, cassava, sweet potatoes there, but it will have to come from these crops. This will have to feed the world that we talk about. And potatoes are one of them, and it will play an increasing role because we talked about a shift in the dietary needs of the customer or the consumer. So potatoes will play a bigger role in future probably than it have now. And how are we going to do that? Because we're producing X amount currently, and there's no more land, so we'll have to increase our ability to produce on the same amount of land. How are we going to do it? So let's have a look at yield gap analysis. What is yield gap? It's a difference between the potential yield and actually observed yield on a farm gate, what goes out of the farm gate. So potential yield is the yield of a cultivar or a crop when grown in environments to which it is adapted, nutrients, seed, and water not limiting, with pest, diseases, weeds, and other stress efficiently controlled. The answer for our demand or question at the beginning of producing more food, we will have to know what's the potential yield, what are we currently attaining on the farm, and what is the potential yield. And this is the yield of a cultivar or a crop when grown in environments to which it is adapted, nutrients, seed, and water not limiting, with pest, diseases, weeds, and other stress efficiently controlled. The answer for our demand or question at the beginning of producing more food, we will have to know what's the potential yield, what are we currently attaining and how can we bring that closer together. But I will talk about that as we go along. The yield constraints, constrained by growth defining factors, and this is carbon dioxide, solar radiation, temperatures, plant characteristics, physiology, phenology, and canopy. Interesting enough, the carbon dioxide, when I was going through the slides again, I thought I will just have a look at what it, of course, I have this number in my head of 300 parts per million. Now that was 300,000 parts per million. Apparently, this is now 412 parts per million. What we're talking about greenhouse gas emissions, this is definitely one of the greenhouse gas emissions, and it is increasing, and with gases as well. This is the growth defining factors. Looking at the calculation as well, how do we calculate potential yield? I think the most correct one is perhaps the crop modeling simulations, like the lentil model that Prof. Martin Stein and his team is using by determining potential yield. Ways of doing it is cultivar trials, like we're doing currently for Potato South Africa in their program of testing the cultivars in certain conditions, and that's another way of determining what's the potential yield, and there's other ways of doing it as well. In practice, the actual farm yield well below the potential yield, and that is two groups of factors, naming the growth limiting factors and the growth reducing factors. The growth limiting factors are water, nutrients, soil in brackets at the right, seed quality, and the new one I found that they're mentioning in the literature is also funds, capital, which can be a limiting factor. The other one, the reducing factors, diseases, weeds, insect pollutants, and so forth. If we take all of that and we summarize just before coming to that, at this stage, this is some work that Prof. Martin Stein and his team have done on crop model stimulations, and you will see pinkish of the red is the calculated, or this is the potential yield versus the actual average yield now for the different areas in South Africa. And you will see that we're still well below potential yield. So there's a lot of space where we can still increase our production, not by increasing the acreage, just by increasing the effectiveness of the productiveness of how we're farming. And I think we're between 25 and 35% below potential yield. So still a lot of space to make up. The next slide is actually just a summary of what I've just talked about. So we have on top to the left, you will see there's the potential yield, and at the bottom left, there's the actual yield. And it is for us to increase that to get nearer to the potential yield, and by managing water, nutrients, seed is the limiting, and the reducing factors, weeds and pests and diseases. And one of my colleagues in the agriculture business always said, farming is sort of a subtraction or a deduction calculation. You start off with a potential yield, and as you move through the whole production season, things happens. There's not enough water, something is deducted. There's not enough nutrients, something is deducted. And at the end of the day, you get the actual yield. So farming is a deduction calculation. So what we're going to do now is just have a look at the limiting factors, the water, nutrients, and seed. There are the three that I just talked about, limiting factors, and we're going to start off with looking at just one slide, having a look at water or water stress. And as you see in this slide, they say that drought is considered the single most devastating environmental stress, which decreases crop production of crop productivity more than any other stress or environmental stress. In my years of being an agronomist, I would say 80% of incidents where I had to go to a farm where there's an issue with growth, it was probably an irrigation or a water limiting or too much or too little issue on that farm. This plays still a major role in what the yield will be, the actual yield. And if we can manage our water better, we will get a higher yield. Sometimes it's possible, sometimes not. But this is still something that needs a lot of attention. If we don't manage, if the plant is under water stress or too much or too little, as I said, what's the function of water? It's very important for transport in the plant, the minerals, the hydrates that's being produced, taking that from the leaves to the fruit or the tuber where it must go, part of the photoplasma, part of the chemical processes in the plant, and also buffering temperature in the plant, temperature fluctuations. And this is just an example of what I've just said. This is what happened in 2016 and 17 when we had a drought. You will see there was a decrease in the average yield in South Africa of about 6 tons per hectare, nearly 12 to 13% decrease in production just because of a water issue that we have. You will see there what will happen if we do not have enough water. Seed or any material, planting material that we will need, and this is true for not just for potatoes, but for any crop that we plant. Good seed is, as the writer did, and that was Dr. Piano Kier, compiled this best practices booklet on handling potato seed. And I think he just left South Africa at this stage. Seed potatoes are more valuable than gold, not only because the cost of seed potatoes comprises the greatest portion of the production cost, but also because seed potato quality is a determining or / limiting factor in yield. The quality of seed potatoes is determined by their disease status, physiology stage, size, and vigor. Unfortunately, I do see a lot of times that people just accept. I always think, it's such a costly thing that we're busy with. 300 Rand a bag of seed now. And if you look at what's the total cost, it times 200 bags is 60,000 Rand a hectare. If you look at a 10 hectare, the cost is more or less the same as a new Toyota Bakkie or Nissan or whatever you're driving. And the question will always be, if you ordered a new Bakkie for yourself and the dealer in 6 months' time bring you a Bakkie with a dent in the side and a smashed window and you hear there's something wrong with the engine, will you take it? No, you will send it back. We must do the same with the bad seed that we get. Don't plant it. It will just give you problems later on, and the yield won't be that great. Okay, going to having a look at the mineral nutrition. There are the 12 that we usually talk about, the elements the macros and the micros, primary nutrients, NPK, secondary, they're all just the macros. Calcium, magnesium, and sulfur, and all the micros that you see on top of there. So we will just have a look at which I think it's perhaps at this stage the most important is nitrogen, phosphorus, potassium, and calcium. I think Duncan will give a bit more attention to the potassium and perhaps go into the nitrogen as well. So I won't be spending that much time on that first three, and perhaps just have a little bit more look at what's happening with calcium and where it plays a role. But just looking at this table, you will see that this first four, they play a huge role, whatever the plant's function is on yield, tuber size, or quality, growth, whatever. So just on nitrogen, you can see this is an uptake curve. There's 5 elements, and just have a look. Magnesium is on the right axis here. So it's in smaller increments, because otherwise you wouldn't see it at the bottom. Uptake of potassium followed by nitrogen, and you will see calcium also there with the phosphorus, the red line at the bottom. But interesting to note here that you definitely do have a peak uptake of most of them from tuber initiation. At the bottom, you will see that's days after emergence, 2.5 months after tuber initiation. So whatever we want to do, we have to do that in the first, say, 10 weeks. But keep the uptake curve of calcium, keep that in mind, which you will see do definitely have a peak just after tuber initiation, and it will go up to 100 milligrams of calcium per day, which if each plant will be taken up. The next one is just on uptake of the potato tuber, and I'm not going to spend too much time here. What I do want to have a look at, and as I move along now through the different elements, you will see that I mention a lot of source, timing, rate, placement, and we talk about the 4R concept. It's the right source, the right time, the right placement. What I'm showing you here is the right amount of N, and this is just work that has been done Belgium, and I think a hell of a lot of work has been done on this. Is what is the optimum amount of nitrogen that you will use. I'm not looking at balanced nutrients now, just at the pure nitrogen. You will see that the optimum years look, say, somewhere around 120 to 150 kilograms per hectare, but you need more than 60. Because you will get an increase. The total amount too is important, and I will later come to other factors here as well. Then they did some split applications, and you see an increase again. If you split, let's have a look at the 150 at the bottom, where you just planted with the 150, and there's no split applications toward the bottom one of the 90 and 30 and 30. You will see increase in production. Still, the total amount is the same, but you have an increase in production, meaning the right rate. So just keep that in mind. And this is just more evident in the work that we've done in the Sunveld, and this is just one of the trials that we've done on looking at fertigation. Now, the Sunveld's name actually tells you what's happening in that area. It's a sandy area. And if I talk about sandy, less than 1% clay in the soil. But my time is getting a bit little. What happened here is that you will look at things like concentration in the soil of the different elements. So this is work we did 1 application per week versus the fertigation of 3 applications through the water per week. And you will see that we get between 25 and 30% increase in yield, being more effective in whatever you're busy doing. The type of fertilizer or nitrogen that you use, just important. The best results that we had in that area was when we increased the nitrate share of the nitrogen to 80% versus the 20% of ammonium. So that's the right type of fertilizer, the right source. Phosphorus, a complicated element, and it's more like politics than anything else. I'm going to pass that. Potassium, yes, I said Duncan will have a look at potassium more than I will do, but we call that even the anti-stress element, playing a huge role in the regulation of the transpiration. When it's low, if you have a look at the left at the bottom, you will see as the potassium decrease in the dry material, the more transpiration take place, and you will need more water, but the plant can't really react that fast to changes in the environment. Function of potassium is the transporter in the plant, but as I said, I will not give that much attention to this elements. Coming to calcium, a difficult element to get into the plant. And like Prof. or Dr. Nick Combrink always used to say, calcium is like the guys traveling. The one guy just have a backpack, moving easily into the trains, getting off, moving through the passengers. Calcium is the other guy with 2 suitcases, one in each hand, trying to get onto the train. Difficult to get into the plant, and it's just able to move upwards in the plant via the xylem. So no reverse gear, just going upwards. Now, another thing about calcium is for potatoes, doesn't move from the main root system into the tuber. Calcium taken up by the roots, the main root system will move upwards, and the calcium in the plant, in the tuber, will only get into the tuber via the stolon, calcium taken up by the stolon, or the roots on the stolon, the calcium taken up by the tuber itself. But the calcium taken up by the skin or through the skin of the tuber only go as far as the cortex or the outer 5 or 6 millimeters. Then it will stop there. And the calcium moving in from taken up on the stolon or the roots there will go into the tuber. in the medulla area. It's not just a give more calcium. Where will the calcium be? So it's the right placement of the calcium. That's important. And then when it moved into the plant, it's still a question, will it go as calcium pectate or will it just go into the vacuole as calcium oxalate? So another difficult one, Dr. Estelle Kempen and her team did some work at Welgevallen on the timing of the higher calcium. You remember I've shown you, as I mentioned at the beginning, calcium do have a peak tuber initiation where you must increase it, and she found the same. But the thing is, you can't increase it too much in the beginning because then you will have a decrease in tuber initiation. So it must only be after tuber initiation till about 4 or 5 weeks after that. Calcium is not taken up anymore into the tuber. So difficult one, this one we have to work with. This is just an illustration or a flow diagram that we compiled out of the work that's available on calcium. You can download this on the Yara website, and you see at the bottom right, here's the website link. It is yara.co.za, and you just go to potatoes and you will find it there. You will always also find this on Potato South Africa's website. I'm not going into this. This is the Yara crop nutrition power brands. The Levas on top is the calciums. The Milas is the NPKs, the Bellas is the nitrogen, Vitas, the trace elements, Jara is our fertigation product, and the Yara Rega is the dual purpose products that's now available. It can be spread or it can be dissolved. It's a new range that we are putting into the market now. I've talked about the 4R nutrient stewardship principles: the right source, the right rate, the right time, the right place. This is what nutrient application is all about. Giving the right source, and I've talked about ammoniums and nitrates. The right place, the right timing for calcium is so important, and the placement where it must be taken up. Sorry, my time is getting a bit, we're moving a bit to the end, and I'm moving over my time now. This is just where we're moving now. This is more currently, it's not that huge at this stage, but I think this will grow. We talked about the nature positive solutions, things like regenerative agriculture, and it's not something that just the green guys or the organic guys are talking about. This is for farmers to have a positive effect on climate and nature, and we'll have to do it to be sustainable. This is just the concurring themes in regenerative agriculture, climate, soil health, resource use efficiency, biodiversity, farmer prosperity. I think something that we're already doing to each extent is soil health. We do a lot of chemical analysis. We know what our texture of our soils are. And just by looking at the soil respiration, which is an easy measurable thing as well, we can really do have an impact on soil health. But the thing is, we must measure it in some sort of a way. And I think this will get more attention in the years to come. So, concluding, mega trends that we see out there will be more people, we will need more food, but we will have to use less land in producing it. We must decrease the greenhouse gas emissions. We must look out for our resources, more efficient with them. By being resilient, sharing our knowledge, and taking hands, creating partnerships within this whole food supply chain, we will be able to get there, be able to produce potatoes for the next 25 to 50 years. Thank you very much.
Okay, my topic today, as I mentioned earlier, is balanced nutrition in horticultural crops. To discuss that, obviously not in great detail because it is a huge topic and one could do a webinar for a whole day on this concept. But for the purpose of this presentation, I think the key points to consider are nutrient element removal by crops, electrochemical potential of the roots, and I will briefly look at an ideal nutrient solution model proposed by Steiner. We will look at excess or unwanted elements in that model, and then we can discuss synergistics and antagonistic relationships, largely due to the form of nitrogen. And then most importantly, energy efficiencies, carbohydrate production, dry matter production by the plants, and then saline growing conditions. If you look at nutrient removal by crops in kilograms per metric ton, I have the three graphs at the top, potatoes on the left, tomatoes in the middle, and watermelon on the right. You can see in each case in horticultural crops, the usage of potassium is invariably always the highest, and then nitrogen. If you look at the table below, there are some other crops mentioned where the potassium and the nitrate in some cases are equal, but generally potassium uptake in horticultural crops in kilograms per metric ton is usually the most or the highest. This was work done by Dr. Oosthuizen. Some of you might remember him. He took superior quality Valencia oranges and he analyzed them. And again, you can see that potassium is almost double that of nitrogen and then of calcium in orange fruits. So the uptake of potassium and nitrogen insufficiency is most important. So what fertilizers are available to us? You all know that it's potassium nitrate, potassium sulfate, potassium chloride, ammonium potassium phosphate. So those first four are all potassium sources. So the potassium is the positive cation, and they are paired with a anion, nitrate, sulfate, chloride, and phosphate. So you need to choose what you're going to use to make certain that you have the correct balance of nutrition around your roots. So the charge and the amount required are both very important. You can go through that list in your own time. You can see urea at the bottom has no charge, but when it dissociates, it will definitely produce ammonium cations, then with probably carbon dioxide and oxygen as anions. The next concept is electrochemical balance. Plant roots need to remain neutral regarding ionic charge balance. For each potassium ion taken up, for example, a nutrient carrying a negative charge must be taken up. It will be nitrate if one uses potassium nitrate, but also other cations, which are important, calcium, magnesium, also cations, they can be taken up to balance the uptake of nitrate. So just keep that in mind, that the charge within the plant needs to remain relatively neutral. The next concept is what they call, or a model proposed by Steiner. It is what he calls the ideal nutrient solution, or the ideal nutrient ratio in a nutrient solution. You see two triangles in front of you. The one on the left are the cations. You've got potassium, calcium, and magnesium, and they need to be at a certain ratio. And then the triangle on the right, you've got the anions, the nitrates, the phosphates, and the sulfates, and they also need to be at a certain ratio. Now, you can influence that ratio depending whether you're using potassium nitrate, potassium sulfate, etc., etc. So by having a knowledge of an ideal nutrient solution, okay, this is hydroponics, but the concept is exactly the same if you're moving to even a soil with a cation exchange capacity, to understand what's in that exchange, which will feed the nutrient solution around the roots, or in a sandy soil such as the sunfelt in the potatoes, where you need to apply lots of fertilizer regularly. You need to be aware of what is the nutrient solution around the roots, and that needs to be balanced, because if it's balanced, your uptake will be active and selective and efficient for the plant. So just keep that in mind. The next concept, the concept of unwanted cations. You can see on the left-hand side in the cations, you've got sodium, such as in a saline or brack soil, and you've got ammonium. They are unwanted cations in this ideal nutrient ratio. And on the right-hand side, you've got the chloride anions, which is also interferes with the balance of the anions, the nitrates, the phosphates, and the sulfates. I'm not saying that chloride isn't required in trace element amounts for plants. It's beneficial. And I'm not saying that ammonium is not required in very small amounts also to regulate pH of the nutrient solution. But in excess amounts, all of those unwanted. In fact, some people say they can be classified as useless salts. The bottom right-hand side, I double circled the sulfate in the slide because a lot of growers will be advised to go chloride-free for certain crops for good reason. And then because it's cheaper, they will apply all their potassium in the form of potassium sulfate. Because of that, because of the high requirement of potassium, they oversupply sulfate, and sulfate becomes an unwanted anion, contributing to the soil cation exchange, or the soil excess, or EC. Just an example of the potassium sulfate. If you look at the first line of this table, you see the orange fruit nutrient export. In other words, the elements in the fruit, you've got potassium at 2.7 kilograms per metric ton, and you've got sulfur at 0.1 kilograms per metric ton, which is a ratio of 1 to 0.04. If you look at the nutrient balance in potassium sulfate, you've got 42% K and 18% S. And if you apply all your potassium as potassium sulfate, you're applying 11 times too much sulfate. And the bottom of that table is the tomato. It's not so bad. It's 3 times the amount of sulfate, which is still in excess of sulfate if you apply all your potassium as potassium sulfate. So an excess sulfate in relation to plant demand contributes to soil salinity buildup, which you don't want, and you're also disturbing the ideal nutrient solution, the anion balance in this case. If you look at that little formula about halfway down, you've got potassium nitrate, and you can have other sources, as I said earlier, potassium sulfate or potassium chloride. So the sulfate and the chloride are perhaps unwanted anions if in excess, but you also need to apply a nitrogen source, and that nitrogen source will always contain some ammonia, whether it's ammonium sulfate or LAN, which is an ammonium nitrate, or urea, which breaks down to ammonium. That nitrogen required by the plant to make up for potassium nitrate will be predominantly an ammonium form of nitrogen. Brenda, if you can just show this. On the left-hand side, we have antagonism. So if you apply excess ammonia, which was an unwanted salt, it competes directly with the other cations, the calcium and the magnesium and the potassium. On the right-hand side, you have a synergistic situation. If you apply nitrate, you have a synergistic uptake of your calcium and your magnesium and your potassium. And you have luxury uptake or sufficiency in uptake of both. Just a few examples of this. This graph is watermelon. You can see the rectangle on the left-hand side of the graph is a 3-to-1 ratio of ammonium to nitrate, and you can see the uptake of potassium, calcium, and magnesium in the grams per plant. And if you look at the right-hand rectangle on this graph, you can see that there's a 3 ammonium to 1 nitrate, and how the uptake of calcium, potassium, and magnesium is reduced. In a young barley plant, you can again see the synergism. The young barley plant is taking up a lot of nitrogen. If you apply it in the nitrate form, you get a synergistic uptake of potassium, and you get sufficiency of both. If you use potassium as potassium sulfate or potassium as potassium chloride, the uptake of the potassium is much less. So the synergy with the positive cation and the negative anion is apparent. In citrus leaves, the table in front of you on the left-hand side is potassium sulfate, potassium chloride, and potassium nitrate as treatments. And if you look at the potassium in the leaf, it's much higher with potassium nitrate because of the synergy, which translates to yield. And Pitt was talking about limiting factors, and when trying to close the gap, one needs to consider the form of your fertilizer applications to help close the gap between actual and potential yield. Last one on this is the potassium content of muskmelon in the leaf blades and the petioles and the roots. So the y-axis is the potassium content. Bars are nitrate, which are the dark bars, and the light green bars are ammonium. And you can see that the uptake synergy is always better using nitrate. We've all heard of blossom end rot, which is a calcium deficiency, but not necessarily a calcium deficiency. It's usually an induced calcium deficiency, and that's often created by an excess of ammonium. So if you look at this graph, you've got the two right-hand side bars, which is ammonium nutrition, and the two left-hand side bars, which are nitrate nutrition, and the blossom end rot, which is the Y vertical axis. You can see that there's much higher blossom end rot using ammonium nutrition versus nitrate nutrition. And that is because of the antagonism of the unwanted salt of ammonium versus calcium. Other examples of induced calcium deficiencies are tip burn in lettuce, internal browning in pineapples, bitter pit in apples, internal browning and hollow tubers in potatoes. That last statement may be controversial to a lot of people, but I maintain that ammonium is in horticultural crops is a pH regulator and certainly not a plant food. Getting to the end now, the concept of dry matter accumulation, carbohydrate accumulation in plants. Nitrates are converted to organic compounds more often than not in the leaves of plants, not exclusively in the leaves, but primarily in the leaves of plants. And light energy drives this reaction, and it is efficient. Ammonium, on the other hand, is converted exclusively to organic compounds in the roots, and carbohydrate from the leaves drives this reaction, and it is energy inefficient. The irony is that the nitrate in the leaves goes via ammonium to organic compounds, but both those steps are driven by light energy. And I'll just read this next statement to you because it explains it quite nicely. The reduction of nitrate to nitrite and to ammonium is predominantly taking place in the leaves of many plants. The critical step, reduction of nitrite, is driven by energy of 6 electrons excited by capturing of light in the chloroplast. The ammonium is then incorporated into organic compounds, and this process is also using energy derived by the photosystem II in the chloroplast. This is energy efficient because it does not rely on consumption of carbohydrates by the plant. On the other hand, ammonium taken up by the roots is exclusively metabolized to organic compounds in the roots. This is achieved by using the energy process of NADH and NADPH derived from carbohydrate energy from the leaves via the phloem. This process always requires the consumption of carbohydrates and competes with other energy requiring processes such as root growth and cell survival when there is a restriction in the availability of carbohydrates. This is energy inefficient and always leads to lower dry matter accumulation, affecting both yield and quality. Just an example or two of that, you can see the two bars on the right-hand side of potassium nitrate, and there's dry matter as the y-axis, the vertical axis. So the efficiency of the nitrate and dry matter accumulation is apparent. And again, this is dry matter accumulation in wheat. The light orange bars are nitrate and the purple bars are ammonium. And the efficiency, or again, biomass of the wheat plants is greatest with the nitrate. And that's due to dry matter accumulation or carbohydrate efficiency. Right, the very last point is in a saline condition. These were pot trials done again by Fort Research SA, Dr. Oosthuizer, and it was done with bananas, oranges, and tomatoes. For each crop, you can see that induced saline conditions, that potassium nitrate always outperformed potassium sulfate and the potassium chloride. Primarily because potassium nitrate, if you give it a relative EC of 100, and if you use potassium sulfate and potassium chloride with nitrogen source, your EC is going up much more in your nutrient solution around your roots. So your potassium nitrate, both of those ions are being used. There's no useless salts around, and so it makes perfect sense to use a product like that in a crop, especially in saline conditions. Right, Brenda, if you can just show this one. This is the last slide. So you've got a nitrate that is antagonistically competing with the chloride, so you can just see how beneficial the nitrate will be, especially in a saline condition. Okay, just to summarize what we've talked about, I think it's very important to remember that your potassium and your nitrogen are the most used by horticultural crops. It's very important to remember the electrochemical balance of roots, so it makes sense to use a positive and a negative, such as a positive calcium, magnesium, and potassium with a negative and nitrate for enhanced synergistic uptake of both. One needs to remember those two triangles, the ideal nutrient solution model proposed by Steiner the sufficiency and selective uptake of all those nutrients. And there's no place for ammonium and sodium and chloride in excess quantities in horticultural crops. It just disturbs the ideal nutrient solution. And most important to remember the energy efficiency and dry matter production. That's what fruiting and yield and cropping is all about. So one needs to make sure that you're using nitrate which is converted efficiently into organic compounds, and not ammonium which is using the carbohydrates which should be going into growth and fruit and yield and quality. And then lastly, in saline conditions, it makes perfect sense to use fertilizer products that will not contribute to the soil EC. So yes, remember try and maximize your nitrates, potassium nitrate, calcium nitrate, magnesium nitrate, and then try and maintain the ideal balance around your roots. Thank you very much.
There is one question.
Okay, let me have a look. Okay, Peter, that's for you. The question is there a link between the nitrogen ratio split and potato varieties?
No, I don't think potato varieties, as you've mentioned now, between crops. You see that in what we've done, with the 80% nitrogen of nitrates versus the 20% ammonium. You see that right through all the crops. So definitely not between cultivars that I know of, potato cultivars that I know of. Soils does make a difference, of course, the environmental conditions and stuff like that, but not cultivars.
Okay. The other thing you mentioned in your presentation was water stress, and that being one of the biggest problems, closing the gap between potential and actual. And, fertilizer application, irrigation, and water management go hand in hand as well. So I think the two, water stress can also be influencing the nutrient, management in the soil, because if you're not managing your water correctly, your plant's definitely not getting the nutrients that it needs at the right time either.
Correct. Leaching, stuff like that, especially in the more sandier soils, the water holding capacity being so low, 30 millimeters in the top meter. In clayish soils, you can go up to 100, 120 millimeters. Huge differences, and horses for courses, as they would say.
Right. Well, that concludes today. We have another webinar in about a month's time on tomato production. So we will send out invitations for that. But thank you very much, Pitt, and thank you all for attending. And I really hope that you took something away today that you can now apply in the field. Thank you very much, and thank you, Brenda.
Yeah, thanks. Thanks, guys.